Okay, so the first thing we're going to review is going to be where the electrons are located in your atom and also how we know that they are located in those specific spots. So what is the evidence that supports that? So electrons are going to be found in very specific three-dimensional spaces called orbitals. And there are four quantum numbers that we define where the electron is. So the energy level or the shell number, the sublevel, which can either be S, P, D, or F, which really describes the shape. So remember, S is circular, P is going to be a dumbbell shape, D gets more complicated, and then E gets even more complicated after that. So, and then each of these sublevels has specific orbitals, which really just kind of dictates what direction the electron is. So it just gets more and more specific as we go. And then we have the spin number after that. So basically, you know that two electrons cannot have the same four quantum numbers because they can even be in the same energy level, the same sublevel, the same orbital, because we can fit two electrons into each orbital, but they will spin in opposite directions. So let's look at an example of an electron configuration. So let me pull out a periodic table and let's look at zinc. Okay, so zinc is right here. So we're going to go from the beginning and basically read off the periodic table until we get to zinc. So remember, the period number will tell us the energy level, and then we have four regions on our periodic table. We have the S block, the P, the D, and then the F all the way down there. Okay, so let's start off with 1. We're starting off with hydrogen, so 1s, there's 2 electrons into S. Remember, you cannot fit more than 2 electrons into S. Then you go down. Now we're in energy level 2 in the S block, so 2s, 2, go across. So now we're in 2p, and then we can fit 6 electrons into 2p6 or 2p. Then we can go down. Now we're in 3 in the S block, so 3s2, go across again. We're now in 3p, and we can fit 6 electrons there. All right, and then we are going to go down to 4, and we're in the S block. We can fit 2 electrons into there, and then we go into the D block. But remember, you subtract 1 when you go in the D block. So it's going to be 3D, and then we count till we get to zinc, and that's going to be 10. So this is the electron configuration for zinc. So remember, we're going to fill up that 4s before we actually fill the 3d, and that's part of the Aufbau principle. So when we look at this configuration, it has 2 electrons in its outermost energy level. So we look at the highest energy level, which is this one. Now, if we were going to decide what kind of ion it will make, well, metals will lose electrons, so they're going to lose electrons from the highest energy level first. Well, this would be 4s2. So if it were to become an ion, we can get rid of these 2 electrons here, and then it would have a full third energy level here. So it's going to get rid of those, and then that would be the new configuration if we were to write the zinc ion. So zinc has a +2 charge, and we can look at the configuration and say, well, it's going to lose these 2 electrons right here. All right. So let's look at bromine. Okay, bromine is down here, and if we write the configuration, well, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then we're back in the p block, so it's 4p, and then 1, 2, 3, 4, 5. Okay, so when we look at this configuration, well, it's less likely to lose electrons, because in order to lose electrons, well, we have 7 electrons already in its outer energy level. So it would be really hard to lose all 7, but it would be very easy to gain 1 electron to fill up that 4p. So nonmetals typically will gain electrons. So since we're so close to filling up that 4th energy level, or at least getting 8 electrons in that 4th energy level, it's more likely to gain an electron and become bromine with a -1 charge. Remember, if you add electrons, you're making a negative charge. If you subtract electrons, you're going to make a positive charge. So bromine will have a -1 charge and become 4p6 at the end. All right, so now there's some vocab terms that you really need to remember for electron configuration. One of those is that what isoelectronic means. So isoelectronic means that they will have the same electron configuration. You cannot have an isoelectronic species if they're just atoms. So remember, if they're atoms, they don't have a charge. So if they do have a charge, then they can be isoelectronic. So let's look at chlorine -1 and sulfur with a -2 charge. So if I look at that in the periodic table, see chlorine and sulfur. So Cl- and S2-. So when I look at this, they're right next to each other. Sulfur normally would be 1s2, 2s2, 2p6, 3s2, and then 3p4. Well, when it becomes a -2 charge, we're going to add 2 electrons to that, and then it becomes 3p6. Well, chlorine, 1s2, 2s2, 2p6, 3s2, 3p, and then chlorine would normally be 3p5, but when it becomes a -1 charge, we're going to add 1 electron to it, and then it becomes 3p6. So these species are isoelectronic because they have the same configurations. So really, if you look at the periodic table, when they become ions, they typically gain the electron configuration of the closest noble gas. So sulfur and chlorine, when they both become ions, will get the configuration of argon. So we could also say that argon would be isoelectronic with all of these. I also know that if sodium became an ion and magnesium became an ion, they would also be isoelectronic because they would both gain the configuration of the closest noble gas, which would be neon in this case. Okay, a couple other things that you guys need to know, like paramagnetic and diamagnetic. So paramagnetic means that they have at least 1 unpaired electron, and they can become a magnetic species. So when we look at our configuration, you really need to look at the orbital diagrams for that. So let's look at, let's say, sulfur and phosphorus. Okay, so sulfur and phosphorus. So what we're going to do, we're going to look at the last part of the configuration for sulfur and phosphorus. So if I look at it for phosphorus, it's going to be 3s2, 3p, 1, 2, 3. The last part is 3p3. I'm only looking at the last part because everything else before that should just be full. So if I do the orbital diagram, this is what I'm going to see. There's 3 orbitals, np. I've got 3 electrons there, so 1 electron going up. And remember, if I'm writing out these orbital diagrams, I do not pair the electrons until all of the orbitals have at least 1 electron in them. So 1, 2, 3. So if I'm looking at this last part, I can see that I have 3 unpaired electrons, which makes it paramagnetic. If I look at sulfur, the last part of sulfur's configuration is 3p4. So if I draw out my orbital diagram, it'll look like this: 1 going up, 1 going up, 1 going up. Now I pair it, so 1 going down. And it has 2 unpaired electrons, which makes it paramagnetic. So I'm just going to look at the last piece of the configuration and then draw the orbital diagram to decide if it's paramagnetic or diamagnetic. So diamagnetic is when you have all paired electrons. Basically, if you look at your periodic table, if it's at the end of a sublevel, it should be diamagnetic. So zinc would be diamagnetic because everything should be full, and if it's full, everything is paired because we don't pair until we have to. So if I were going to be looking at neon, okay, or argon actually, argon would have all of the electrons filling up that last sublevel, which means that everything should be paired. So it would be like this. So beryllium should also be diamagnetic. Magnesium should be diamagnetic. I could also see that Mg plus 2 would be diamagnetic because if I remove those 2 electrons, I'm still going to have a full sublevel at the end, which means everything should be paired. Okay, so ground state versus excited state. So remember, if you remember back to the flame test, if you add energy to an atom, the electrons can actually move up in energy, so they become excited. So the ground state is what they normally are. That's the lowest possible energy level that you would have. So for magnesium, the ground state electron configuration should just be 1s2, 2s2, 2p6, 3s2. These are the lowest energy levels possible. This is the ground state. Now, if it moves up in energy, one or more of these electrons can actually jump up into a new sublevel or energy level. So it could be something like this. 3s1, and one of those electrons jumps up into the p. So that could be an excited state. So one of the electrons will just jump up in energy, or you could have multiple electrons do that too. Okay, so photoelectron spectroscopy is one way that we can actually show evidence of where these electrons are. So it's evidence. So basically, high energy X-rays or UV photons, light particles, can be used to eject these electrons from the atoms. So we use energy to remove the electrons from the atoms, and that's called the photoelectric effect. And if we look at that, the energy is equal to Planck's constant times the frequency. So remember, anytime that we're talking about light, light has a frequency and a wavelength, and that frequency is related to the energy. So these electrons are ejected from the atoms, and then they're analyzed by making a spectrum. And that spectrum shows peaks that correspond to those electrons that are being ejected at certain energy levels. And it shows how many electrons are ejected at that point. Okay, so if the electrons are closer to the nucleus, it's going to require more energy to remove those electrons. So if we are at 1s, those 1s electrons, if I'm looking at this, these 1s electrons are actually going to be closer to the nucleus, which means that they're going to be the hardest to remove. The 2s electrons will be a little bit easier because they're a little bit further away. So remember, all of this stuff relates to Coulomb's law because College Board is obsessed with it, and really we just need to think about how the attraction and repulsions come into play when we talk about removing electrons or adding electrons to an atom. Okay, so let's look at a PES. Okay, so this is what you'll see. More than likely, some of the PES will look a little bit different, but on the y-axis you have the relative number of electrons. So basically, the higher the peak, the more electrons there are at that point. And then on our x-axis we have energy, and you need to really watch the direction of the numbers. So right here, this is a higher energy than over here. So these electrons required less energy to remove them. Okay, so let's write out the electron configuration. Basically, what you're going to do is you're just going to read from the beginning. So from the highest energy level, we should have the electrons that are the closest to the nucleus, and we just read. So we have 1s, that would be the first one, okay? And if I'm looking at the scale right here, this should be 1s2. And if you look right here, this one is 3 times the height, so it should have 6 electrons. This one should have 2. All right, so the next one would be 2s2. So if this was half the height, it would be 2s1. All right, so now we go to the next one. Well, it's 2p6. And then we go to the last peak right here. That should be 3s2. Because it's the same height as this. Okay, so this is the electron configuration, so I can simply look up on the periodic table to see which element this is. Okay, so 3s2 would be magnesium, so this element should be magnesium. Okay, so, and then it says, why is the 5.31 peak higher? Well, that's because there are more electrons there. There's 3 times the amount of electrons as these peaks. It's going to have 6 electrons. Okay, so the questions that you might see would be questions just like you saw here. Identify the element, write out the configuration, which electrons correspond to which peaks. But they might also ask you a question about like comparing elements. So which of the 1s electrons will be higher? Basically, if you're comparing oxygen to fluorine and you're looking at 1s electrons, well, they're in the same position. However, oxygen has 1 less proton than fluorine. So anytime that we are looking at different elements and we're trying to compare them, compare the PES diagrams, well, the element that has more of a nuclear charge will have a higher amount of energy. It requires more energy to remove those electrons than on something that has less protons. So let's look at another example. Okay, so how many unique peaks should we see for aluminum? Which electrons correspond to the largest energy? Which peak will have the greatest intensity? So let's look at the periodic table. Let's look at aluminum right here. All right, so let's write out the configuration for aluminum. So we're at 1s2, 2s2, 2p6, 3s2, and then 3p1. Okay, so now if I'm answering the question, how many peaks should I have? Well, I should have a peak here, 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 and here. So I should have 5 peaks on that PES diagram. Okay, which electrons correspond to the largest energy? Well, the first peak, or rather the 1s peak, should correspond to the largest amount of energy because it's closer to the nucleus, so those electrons are harder to remove. So the 1s electrons. Okay, which peak will have the greatest intensity? Well, that should be the one that has the most electrons. So that should be the 2p6 peak, or the third peak. Okay, so an element in the third period of the periodic table produces a PES that has 3 peaks, 2 to 2 to 1 ratio. So the height would be 2 to 1. What is the element? Okay, so let's look at a periodic table. So we're in the third period, and we need to look at the peaks that we'll see. So if we're somewhere here, well, 1s2 would be the first peak. Okay, then 2s2 would be the second peak. And then, hold on, let's pull the question up again. Okay, so I believe this is actually supposed to be the second period, not the third. Yeah, so that's the second period. So we have 3 peaks. So the next one would have to be 2p, and then it says it's a 2 to 2 to 1 ratio. So we have 2 electrons here, 2 electrons here, but only 1 in this one right here. So those should be my 3 peaks. And if I look it up on the periodic table, that should be boron, because 2p1 would be boron. All right, so all right, and then which peak should have more energy for the 1s electrons, sulfur or chlorine? So if we look on the periodic table, we've got sulfur and then we've got chlorine right here. Which one should have more energy to remove the 1s electrons? So even though the 1s electrons are in the same spot, essentially, if I look, sulfur has 16 protons and chlorine only has 17. So that means that chlorine has more of a nuclear charge. So if I'm trying to remove those electrons, since they're closer to those 17 protons, the 1s electrons should have more energy, because it should take more energy to remove them because of that additional electron or proton.